Okay, dear friends, we started looking at how to implement gates, NAND gate, NOR gate, or inverters using MOS transistors. And we said that typically we use this transistor here, and this transistor is MOS. So since there is no current going through here, that's an advantage. So there is no resistive loading, for the next stage. So or for the previous stage here. So that's an advantage here. And but of course there is going to be capacitive load still. So that will be affecting our fan out. So fan out will be limited not by the current driving capability, but how fast we can turn this transistor on and off due to gate to source capacitance. So here the load can be a resistive load, but we said that making the resistor in the CMOS is very area consuming, because you need to make a resistor. So since this resistor is going to be large, you cannot really do this like a long metal line. So we need to do this maybe kind of resistance. Okay, so a resistor is going to be made like this, so between here and here. Getting large, obtaining large resistance requires large area, so not feasible. Okay, therefore instead of resistor we can use what we call nonlinear resistance or active element here. Okay, so this is called active load. Okay, nonlinear resistance and active load. So there are different versions of this, with advantages and disadvantages. We will be talking about that. Eventually, we will be replacing that with a PMOS transistor. Okay, so the load will be PMOS transistor, and we'll see how advantageous it is. It's going to be the best, and that will be the CMOS inverter. Okay, so we started our analysis with resistive load and MOS inverter, and here we have seen the slide before, and then as you see, we filled the form. So if the voltage is below VTN, then the transistor will be off, and output is going to be V output high and VDD. Okay, so so it goes to VDD rail. However, if the input is V output high, maybe a different color will be better. Not this one, I don't know, maybe this one. So if the input is this, then output is going to be something larger than 0. So we can calculate that. We know that in this region, number 3, Mn is in linear mode. So since Mn is in the linear mode, we can write the linear equation of the transistor and then solve it. If you solve it, our goal should be to make the output low, you know, we like to set the output low to be below the threshold of n. Okay, so a value like, you know, this one is preferable. You know, if you can make it 0.5 volt, that's very convenient. So that you know that the next gate is going to be, you know, that this is how we connect the inverters together. Okay. So if this one is, let's say, low or high, let's say this is VDD, then this will be V output low, and then for the V output low, this should be V output high, which is going to be VDD again, if this one is below threshold voltage. Okay, so that's how we design, and we select the value of RL and also MN transistor equation. So you know, I did this transfer curve here quickly, but I guess in the next slides we can do this one more time for better analysis and see how it can be obtained from the graphical analysis. Now we can look at the output high or input high, input low definitions. So the definition for output high and input high is clear, I guess. Like when input is 0, input is 0, this is called V output high, which happens to be VDD. And then when input is V output high, the corresponding voltage here is called V output low. And we want this V output low to be, of course, lower than threshold voltage. So the input high definition is not very clear in the drawing. So we know that up to V threshold of VTN, this is going to be VDD. And then, you know, for this value of VDD, this is going to be V output low. But what about input low and input high? So input high and input low is in fact determined as the value here where the slope is -1. Okay, so maybe I should select here a little bit larger. Okay, so the point here, slope -1, is the point we define this value as V input low, and this point is defined as V input high. So again, this is slope is equal to -1. So finding those values, those points are not, are not that difficult, but it's tedious. You know, it takes a lot of effort. So, but it is possible to obtain those. Okay, so how can we obtain that? Let's say for this one, input low, it is a little bit easier. Okay, for the input low. How? Because we know that for that case, these are the solutions. So slope -1. So we need to write the equation here, V in and V out equation. You know, we know that V in V out equation, I mean, we know that we have V dd minus, or VDD is equal to V out plus RL IDS. So, and then we also know the equation for this transistor. Now, for this transistor, I think maybe we mentioned that you know, in this region here, transistor is in which mode?
Saturation.
Yes. So this is in saturation. You know, we are talking about voltages around, like, you know, this value or this value or this value, like high voltage. Okay, V out is high because we know that VDS is also equal to V out, right? So therefore, transistor should be in SAT. So I can write the voltage equation for the transistor. So that equation is going to be how? I ds is equal to Kn divided by 2 V gate to source, okay, which is equal to V in minus V threshold of N square. So this one is V gate to source. Okay, so I don't need to write this, no need. You know, those are necessary to maybe find RO. Well, those are secondary effects. So here, if we can write, you know, knowing that IDS is here, IDS is here, if we can write the equation, VDD is equal to V out plus RL times Kn divided by 2 V in minus VTN square. Okay, so here we obtain an equation, V in V out equation. Okay, so therefore I can find what? I can find here the you know, take the slope. I mean, if we can write V out in terms of V in and make it equal to -1, then that's going to be giving us the value. Okay, so you know, we can say one way is this way. You know, I'm going to do this maybe standard way first, but then there are easier, tricky ways to solve this thing. But V out is going to be equal to VDD minus RL Kn divided by 2 V in minus VTN square. Okay, so if I take derivative of V out divided by dV in, this is going to be RL times Kn divided by 2. 2 will cancel, and then V in minus VTN. So this is -1 is the equation, and therefore we can find the value of V in for this case. And what is that value of V in? -1 divided by RLKN plus VTN is equal to V in. Is this correct?
Hocam derivatifini alırken zaten eksi yok mu başında RL ifadesinin?
Yes, there should be minus sign here. So this is going to be plus. You're right. Thank you. Anything else? So this is correct, right? I mean, this seems correct. So finding this one is relatively easy, but finding input high is not that easy. Okay, so we need to use partial derivatives, and then for input high. So instead of spending time on this, maybe I will upload the solution. Okay, so this value of V in is equal to V input low. Okay, so determining V input high takes more time because here for this value output is low as MN is in linear mode. Okay, so notice here that when output goes low, in this region, MN is in linear mode. So in linear, the equation IDS is equal to Kn. Here V gate to source minus V threshold of N, V drain to source minus V drain to source square divided by 2. Okay, so here this one, notice that this one is V in and this one is V out. So the equation becomes a little bit more complicated than V out. So instead of solving this, easily, like making one equation and then trying to find the derivative, like this is not going to be like solving it this way is not going to be that easy, like writing one thing. So partial derivatives are used for that kind of solving, and then we obtain eventually that we input high value. So again, instead of solving it here, I will be giving you a handout maybe when on how this is solved. But basically, maybe I can just give you a feeling of it. We will be writing this IDS in terms of again, like here VDD minus V out divided by RL. Okay, so if we take partial derivative of d IDS divided by dV out, then this is going to be simply minus 1 over RL is going to be the value. So for the other one, this is for the resistor, coming from the resistor. And the other one, we need to do derivative of this, partial derivative of IDS divided by partial derivative to V out, and then plus partial derivative of IDS divided by partial derivative to V in. And then from here, we can write V out divided by V in, and obtain that, and then we'll be finding that out. Okay, so let me do that and then give that as handout. Okay. So the method is tedious, takes time. To solve. So I will give a solution. And typically in the exams, we don't want you to go through this long solutions. So the general operation is shown again here, and I think we did this slide when we drove the load line. So maybe this is given again here, so I can go ahead and then give you maybe some more drawings here. I mean, this is not really drawn nicely. For different gate to source voltages, we obtain maybe different values here, and the load line is going to be determined here. So this is for VDD, and this one is VDD divided by RL. Okay, so maybe I should erase this one and this one and draw it again. So this will be more like this. Okay, as you know, this is going to be sorry, fictitious line. So for different values, we can solve this one. So this is up to VTN. So up to VTN, this is going to be the solution. So this whole thing, is point A. This is corresponding to point A, because this line is the line where V gate to source, which is equal to V in, is less than VTN point. So there are multiple points here. So the second one is going to be maybe this one. And this one, the voltage needs to be determined here, VDS, because V out is also equal to VDS. So that second solution is going to be somewhere around here. It's not really, shown nicely. This, maybe I should erase this and draw this again later on. You know, from the values here, we can determine the voltage. You know, if that is VTN, the 2 volt maybe is going to be somewhere around here. Okay, so that's point B. And then another solution is going to be point C. Maybe I should select this one, C. So that voltage is going to be about 2.5 volts, maybe around here, right? It's between VDD and this one. So depending on the other voltages, we can draw this one maybe. This is going to be D. And then the D is going to be maybe somewhere around here. And then finally, maybe this one, E. Okay. So that E is going to be around here. So the function or transfer function is going to look like more like this. Okay. So this is for 2 volts. This is maybe for 3 volts, 4 volts, and 5 volt. And 5 volt is V output high, as you know, because this is VDD, which is V output high. So corresponding value here is going to be V output low. So if the graph is drawn nicely, that's what is going to be happening. So now that we are in this graph, I'm going to show you another load line. So if the load line or RL is larger, okay, let's say if this is the load line, okay, VDD divided by RL prime, okay. If RL prime is larger than RL, okay, then the graphic, you know, will reach to lower values. So this is going to be then the graphic. Okay, so this is going to be corresponding to, this is corresponding to RL prime. And this one, oops, this one corresponding to RL. So the transfer function we can play, and then this is going to be the other value, V output low prime, okay, new output low. So, but you know, making RL prime larger is even more difficult, okay, even more difficult in IC, integrated circuit. Okay, so and that's how we obtain the transfer function using load line approach. You know, we can look at the power dissipation. Is there a question for the above, or this one? Okay, let's go to power dissipation then. You know, for the power dissipation, for the TTL, we only looked at the static power dissipation for the TTL. But here we will look at also the dynamic power dissipation. Okay, so this one will be becoming more important with the most devices. You know, static power dissipation is the power dissipation, you know, when the output is high and output is low. Let me select a different color here. Static power dissipation is the power dissipation. P static is going to be P when output is high, P when output is low, divided by 2. Okay, so this is what we learned before. When output is high, you know, P output high occurs when? When does this occur? When V in is equal to P output low or 0. Okay, so in both cases, the transistor is off. So power dissipation is calculated from VDD times IDS, and that value of IDS is equal to 0. So therefore, this is going to be 0 watt. Okay, but what about P output low? When output low case, this is when V in input is equal to VDD, and for this case, you know, this is going to be VDD and then the current drawn from a supply. The current drawn from the supply is going to be IDS, or we can find it from the equation if we know V out. It's going to be VDD minus V output low divided by RL. So from here, we find V output low when it is, you know, remaining in there and staying in there. So, you know, if you know V output low, let's say 0.5 volt, then you can calculate this easily. And then we say static power dissipation is the, you know, average of this. Why? Because we assume half of the time output is high, half of the time output is low. Okay. So I mean, that's what we did for the TTL, RTL. For TTL, DTL, and RTL, we only considered P static. But for the most devices, as it was dominant, for most devices, P dynamic cannot be ignored. Okay. In fact, when we when we see the CMOS, we will see that static power dissipation is going to be 0. Therefore, we have to consider dynamic power dissipation. So, you know, if we start looking at P dynamic, the dynamic power dissipation is going to be, you know, when the device is switching from high to low, low to high. you know that this device is going to be connected to another maybe device, and we can, you know, connect many devices here, right? So there's no IN is 0. Since IN is 0 here, IN is 0, so we can connect many. So this means the load, C load, is going to be critical thing. And when you charge a capacitor and discharge a capacitor, maybe you learned from your previous courses also that, you know, there's going to be, let's say you have a switch, and then try to load and this, you know, charge and discharge this capacitor. There's going to be power dissipation, and this power dissipation, maybe we can calculate this later on for the CMOS, but is going to be related with frequency of operation, frequency of switching, and CL and VDD square. Okay, so supply square of the supply voltage. So this is going to be the power dissipation during switching of the gate. Okay, because CL, switching of the gate, when CL is charged, is being charged and discharged. I mean, the power is not dissipated on CL, but it is dissipated on the transistors while it's charging and discharging. So let's say this transistor becomes off, but you still have, you need current to come and then charge that C load. So, I mean, in static power, we say this is 0. But while this is charged up to VDD, there is current. So that current times VDD is going to be creating our power dissipation. So, I mean, we will come to this maybe later on, but then the total power dissipation, power total, is going to be P static plus P dynamic. Okay, now that we mentioned about this here. Okay, so maybe I should erase this. This is not definition, but that's the case. So let's look at the fan out now, another thing. So here, as we mentioned, IN prime is equal to 0. IN prime is equal to 0. So, however, we have capacitances here, C in, let's say, and then, you know, there are these capacitances here. C in, let's call it C in prime. Okay, gate to source capacitance. The value of that we will be calculating. So, you know, the load here is not resistive load anymore. This will be N times C in prime. So that's going to be C load. Okay. So so the N max is not limited by ion prime. Okay, ion primes. Okay, so therefore, in terms of current driving capability, N is going to be infinity if only currents are considered. Okay. However, we cannot say N is infinity. We cannot say that N is infinity as N is defining CL, and CL limits our switching time. Okay, so the transistor off and on time is going to be determined by that CL. So if F max is determined, so you know how fast we want to switch this gate, then N max can be determined. Is that right? I mean, is that clear? I mean, so if Vn is switching, you know, high and low and high and low and high and low, you know, so sorry, you know, they are not equal to each other, but NV out will be like this, you know, maybe this is going to be switched, and then this will be switched high, and then switched low, switched high. Okay, so if this one the frequency is increased, then we don't have time to turn this off. So therefore, you know, we need to, if this is given, if given, okay, then you know, this time period is going to be depending on CL, and the CL will be depending on this N. Therefore, we need to be determining a maximum fan out. Is that okay?
Yes.
Okay, so what are these values, Cn prime, okay, for each device? We will be, you know, seeing this, where it's coming from, but I like to give a break here, maybe continue with those capacitances after the break. Is that okay?
Okay hocam.
Yes.
Okay, let's continue. We said that the advantage of using MOS transistors for for implementing gates is that there's no gate current. So IG, sorry, I gate is equal to 0. So that's the advantage. Therefore, I in prime is equal to 0. So, but we said that due to the capacitance, input capacitance, we have a limit. I mean, we cannot just connect, a number of, like infinity number of gates at the output, because then it's going to increase the capacitance. And if the capacitance increases, the operation frequency is not going to be that high. So if you're operating your microprocessor at 10 megahertz, that's okay, no problem. You can connect many. But if you start operating the transistor or the microprocessor at maybe 500 megahertz or 1 gigahertz, then it will be creating some limits. So that's what you need to know. When you look at the device, where is that capacitance coming from? We can do this analysis in detail, but we will be noticing some straightforward cases here, and depending on the operation, things will be changing. But this, here, if you look at the NMOS transistor, as you know, this is bulk. So there is a capacitance here. We call it capacitance source to bulk. Okay. So the capacitance source to bulk is in fact here. This is the capacitance. So see source to bulk capacitance. And here, due to this diode, drain to bulk capacitance occur. So, and that value is bulk is P. So I think I drew this wrong. Bulk is P, so this will be like this. And this one is probably going to be not like that. So we like this. Sources N. So C, drain to bulk. So that's going to be one of the capacitances. But if the transistor is in saturation in SAT, the capacitance here is going to be, let's say this is like minus N. There's going to be capacitance here. Maybe I shouldn't draw it in there. I should draw it in here. So there's going to be capacitance here. C, gate to source. Even in that case, here, this capacitance area, there's going to be C, gate to drain. Okay, so C gate to source is going to be here, and then C gate to drain is going to be here. Okay, So we won't go into too much detail here, but eventually, especially for this course, you know, we'll see that at least we know this much. We connect this electrically together. So this case is cancelled. Shorted. So this is, you know, shorted, not contribute. Okay. And you know, we will say that this C in, okay, C in, or I can say C equivalent, is going to be about W times L times C oxide. So the C oxide here is oxide capacitance per unit area. Okay. So that's the value that we also use in our current calculations, I guess. Yeah. So I mean, basically, when we consider this device here, we can say that this is a device like this, right? So this is the device. So this is the length. And then this one is the W. So, I mean, the total area is going to be the effective capacitance, okay? C equivalent or C effective capacitance that can be considered as the load. So we know that this value is connected to gate to drain, but you know, that's coming from the also effectively that will be also included in the capacitance that needs to be charged and discharged. And this looks like at the output node, but we can also add that to the equivalent capacitance. But we will be ignoring that because that's negligible. In summary, that's what we will be using this as this one. Okay. So this value is is going to be permittivity of oxide divided by T oxide. T oxide is this thickness, T oxide, okay, and permittivity of oxide is relative permittivity of silicon dioxide times permittivity of free space. So I mean, for this course, I think this detail is enough. That's what we will be using, and this is how we will be considering the load capacitance here. Okay, so this will be our load capacitance. So when we look at this, when we say the gate capacitance, C gate will be approximately equal to W times L times C oxide, where C oxide is permittivity of oxide divided by T oxide. Okay, this is gate oxide thickness. And the load is going to be equal to, the load will be equal to N times C gate, and N is fan out number, and this fan out can be maximum fan out or doesn't have to be maximum fan out. And so the charging, when the input is switched high and low, the discharging at the output, this is going to be high discharging, and then it will be charging, discharging, and this timing, and this one, if let's say T divided by 2, T divided by 2, so F will be equal to 1 over T. Okay, so if we want to do this switching 50% duty cycle, assuming that this is 50%, okay, so T divided by 2, T divided by 2, then for each case, T fall should be smaller than T divided by 2. T rise should be smaller than T divided by 2. Okay, so the minimum of those two, or the maximum of those two, should be considered while estimating the maximum frequency of operation. So how can we determine those values? The charge uptime and charge downtime. So if this is input, this is output. When inputs goes from high to low, we know that for low, this becomes off. Okay, when T is equal to 0 plus. So T is equal to 0 plus. What is this voltage value? VCL. VCL 0 plus.
VDD?
Hmm?
VDD?
No. Initially, when this was here, when input was 5 volts, output was V output low. So we can call this thing V output low. So that V output low, maybe I should draw this here. That's what it starts from. V output low. Okay, so from V output low, this will be charging through VDD. Is that okay? So VCL at infinity, it will be VDD. Okay, so therefore, what about the states of the transistors? T is equal to 0 minus M. Mn is linear. And T is equal to 0 plus, Mn becomes off. And that's what happens. And then we can calculate the capacitance equation. That it's V final minus V final minus V initial e to the power minus t divided by tau. Okay, and this value then is going to be VDD minus final is VDD minus V output low e to the power minus t divided by tau is equal to RL times CL. Is that clear? So if we say that rise time is about 3.5 times tau, then this is going to be about 3.5 times RC times RL. Sorry. RL CL times, sorry. Okay, and then this CL is equal to N times C gate that we calculated. Okay, so that's how we find. I mean, V out is equal to VC. VC of L. So our T divided by 2 should be larger than TR for proper operation. So some people calculate this, you know, going from 90% to 10%. Okay, so going from 90% of the maximum to 10% is also another criteria to look at it for TR. TR calculation. Okay.
Hocam,
So yes.
tam tersi olmamalı mı? Hani %10'dan %90'a gibi düşünmüştüm ben ama.
Tam ne olmamalı?
Rise time olduğu için %10'dan %90'a çıkışı gibi mi?
Yes, yes. Oh, sorry. Yes. I mean, for the output, you're right. This should be the other way around. Yeah. 10% to 90%. Thank you. So how do we calculate that 10%? So from here, 10% to 90%. So, you know, this value, let's say V1, this one is V2. V1 is equal to V output low plus 10% of VDD minus V output low. That's how you calculate it. Okay, and then if you want to calculate V2, it's going to be VDD minus 0.1% of VDD minus V output low. Okay. The voltage swing, you know, this is called the voltage swing. V swing. Output voltage swing. Okay, so that one was the straightforward one. The other one is this case. So let's say T is equal to 0 minus the transistor, this is the case. What is the transistor state? So this is for the input. Let's say it goes to 0. Initially it was 0. So T0 minus, what is the state of Mn? Off. Why? Input is 0 volts. So what happens when at 0 plus Mn? So there is a capacitor here. This doesn't prevent the output to switch. So this is T0 plus time. So our input is VDD. Okay. But then capacitor keeps that value. So initially it will be at VDD. Okay. But then the capacitor will start discharging due to your transistor. And the transistor will discharge through here. Initially, transistor will be in SAT. Initially. Why? Because V drain to source will be larger than V gate to source minus VT of N. What is V gate to source? VDD. What is VDS? VDS 0 plus. It's equal to VDD also. So initially SAT, then Mn goes to linear. So when the output voltage starts decreasing, the transistor is not going to be providing this much current anymore. So it will be reduced. So eventually, this transistor wants to go like this. From here, we output. It will start from here. It will be discharging. So, the target, the final is going to be like this, but it will not be really reaching to that final value because the current will be decreasing and decreasing. So basically, initially it will be discharging very fast, almost like linear. Okay, fast and linear. Fast and linear. But then it will be discharging like this, okay? So, and the minimum value that it will go is going to be the output low. So in the time scale, that's what is going to be. So finding that value is not that easy. So if we assume that, so here the transistor Mn is in SAT. So the discharge happens fast. So if we assume that this will be the case and then it will continue like this, this is what is going to be happening. Sorry, it's so messed up, the drawing, but okay. So this will be maybe the final one. Okay, but we know that in reality, this thing changes the status. So maybe this will be another V final. Okay. V final 2. So here, this is not really easy to determine. Okay. So, but we typically do an estimation here. And then, you know, we say that this 10% compared to this 90%, okay, is something like, you know, if you look at this value, okay, if this would be T1, this would be T2. Maybe this is I don't know, T0, I would say. This is not the T0, but let's call this thing T1, T2, and T3. Okay. So we say that the real thing is T fall is between, in fact, T3 minus T1. But, you know, we can say that T fall is about 2 times T3 minus T2. So we can assume that the current here is kept in SAT. Okay. So we can find the value, okay, T2 can be determined assuming IDS remains in SAT, because if that's the case, then we can calculate VF1. Then, okay, after finding this, we can then assume that T fall is about 2 times T2 minus T1. So either we use simulation tools to determine that timing from 90 to 10%, or we do this estimation. And typically in the exams, you know, we say, you know, find out this, assuming that the transistor remains in, you know, in SAT all the time. Or we can say that assume that the transistor current is fixed and half of D SAT and always remains like that. So that's also a good assumption, because it you know, it's consistent with this 2 times thing. Okay. So I mean, another alternative is for the assumption maybe I should I will be writing it here. Another for the assumption is that Mn remains in SAT, but IDS or discharging is taken as IDS SAT divided by 2. So then I3 minus or T3 minus T1 can be calculated. And assumed to be T fall time. Okay, so I mean, there are different approaches here for the assumption, but in any case, I mean, of course, the best one is to assume that or to use the simulation tools, right, for this thing. I mean, for us, simulation tools are going to be very useful. Here, we can also assume that that current is constant and RL is ignored. So then, you know, this will be maybe linear discharge. Okay. And maybe this is the actual thing. And so, you know, like coming here and then calculating this one from VDD down to 0 is another thing. Here we can say that if IDS is assumed to be fixed current, and then RL is ignored, okay, then capacitor, the timing wise, is going to be equal to a linear discharging VDD minus IDS SAT times delta T divided by CL. So delta T is going to be this delta T. So, I mean, there are different approaches here to estimate this. This is going to be estimation anyway. So if we ask this in the exam, either we tell you your estimation method, or we will be telling you how to estimate this. So, you know, from here we find T fall, T rise, and V fall. So this is going to be then the maximum frequency of operation is going to be 2 times maximum of T rise and T fall. Okay. So this is if 50% is considered. Okay, so if, let's say, this is switching off very fast, but then rise time is very long, then, you know, still we have to use the worst case of this. So if the 50% cycle is not enforced, but typically this is not the case, then you can say this is going to be T rise plus T fall. Okay. But this one is better assumption, because we cannot switch the clock frequency due to cycle. I mean, this is rare. Is it okay? I know it's confusing. what is what, but you know, I wanted to explain you the general approach. Okay, maybe you need to look at this again and digest it. Maybe you can look at the last year's exam questions. You know, this will be the subjects of the next I don't know, well, how do we call midterm 3 and 4? Not for today. Okay. How can we make a NOR gate? You know, here, if we place the transistors, you know that we consider these transistors to be acting like a switch. Okay. Let's say one of them is low, the other one is low, 0 volt, 0 volt. What are the transistor states? Let's say this is MA, this is MB. This is going to be off. This will be off. What about output?
VDD.
Yes, so it's going to be high, basically. Okay, so if one is low, this one is high, then MA is going to be still off, but MB is going to be in linear. So output is going to be low, or the output low. That means it's going to be low. Other case, high to low. Again, the output is going to be low. That's going to be low. This time, this will be linear. This one is going to be off. But if both of them is high, output is going to be still low, but it's going to be output low divided by 2 maybe, you know, because both of them are drawing current, but it's going to be low. So both will be in linear mode. But in you know, in principle, you know, this is not exactly 2. I mean, this will be smaller than the output low. You know, as it doesn't go linearly, but it will be close to half of it. Doesn't matter. This is called NOR circuit. So basically, this will be looking like a NOR circuit. A and B, Z. Okay. So this can be considered as a switch, another switch. So you need to get used to this switch concept. Okay. So this can be resistor or load. You know, we could put here transistor also, as we will be seeing later. Clear? A or B bar. This is how we can obtain NAND. It's very simple. As you see in the BJTs, we used to have many transistors around. Here there are 3 components here, you know, the load and 2 transistors. Much simpler than TTL. Because there were many transistors involved. Here, we can, you know, look at this again in the same concept. Switch and switch. Vout, VDD, RL. Okay. So if low and low is entered, both transistors are off. So output is going to be VDD or high. Okay. If low and high, still current cannot go. Okay, again here IRL is going to be 0. So high, VDD, high, low, again high, it's going to be VDD because IRL is going to be equal to 0. What about both high and high? Output will be low. I don't know, that value of low is going to be called the output low. IRL will not be equal to 0. So output is going to be low. Is that clear?
Hocam,
This is NAND gate.
yine bu durumda da output'un normalden biraz daha yüksek olmasını mı bekleriz?
I mean, that value, yeah, of course, compared to inverter, this can be a little bit larger. Because there's going to be here VDS. There's going to be here VDS. Okay, VDS A, VDS B. So V out is going to be V out. V output low is going to be equal to VDS A plus VDS B. And then both of them are in linear mode. Linear mode. But you know, we design so that this whole thing should be lower than V threshold of N. So as long as that's lower than threshold of N, it's okay.
Hocam, when, for example, when B is high and A is low, what is the state of the transistor B? MB.
You know, one side is when B is low, you know, there is transistor state is is not clear because when B is off, I mean, eventually it's going to be off again. Like it's going to be at the edge of forward active, but you cannot really tell what is happening because this is floating. So your 5 volt here. So let's say this is 0 volt. This is 5 volts, right? So this is off. So this is floating. So you cannot have the voltage here appearing. So it doesn't matter. I mean, this voltage is going to be in there, but no current is passing anyway. So we don't really ask you to write the state of the transistor in that case. But you can say it's in the linear mode.
Teşekkürler hocam.
But you know, it's not critical, so sure. So you cannot really say what is the state of this transistor. If this is here, this is floating. Okay, but you know that no current is passing. IDS is equal to 0. Okay. One last thing is, you know, the nice thing here, we can do very complicated circuits here with this idea. And let me do that in 1 minute. This will be interesting. If Z is equal to A or B dot C D plus E bar. Oh my God, this looks very complicated. Okay. So, this is very easy to implement if you know the idea, VDD. So you know how to make this OR gate, either A or the other rest of the circuit. And you know how to make NAND gates. So this will be B, this will be C, and then AND OR of D and E. Huh? What do you say? Isn't this nice?
I think it is nice, hocam.
So this is what we will be, you know, doing for multiple input cases or more complicated circuits. So that's it. So if A is high, we know that output is going to be low. So A is high because of this. If A is high, then output is going to be low. So you don't need to look at even B, C, D, okay? A is 1, then Z is going to be 0. So the transistor is on means, you know, it pulls this down. Okay, so maybe I can put here. So I'll stop here. You know, this load can be different load. You know, load can be an active load also. Not, it doesn't have to be resistive load. So I'm stopping here.
Hocam bir şey sorabilir miyim orada?
Yes, sorry.
Sağ alttaki DE NOR olmadı mı? Did I make a mistake here? Yok hayır, sağ alttaki DE OR olması gerekmiyor muydu? Biz NOR yaptık sanki.
No, but the NOR is connecting here, but this is together in the line. Like inside is OR. Yes, you are right, but you know, eventually, you know, this needs to be pulled down. Maybe I shouldn't mess up here. I mean, if you look at the case here, let's say A is equal to 0, B is equal to 1, C is equal to 1. If D is equal to 1 also, then Z is equal to 0. Okay. If you know, one of them is 1 is enough. E is don't care. right? I mean, here, if this is 1, this is don't care. And then this is 1, this is 1. Output is going to be, low. Is that okay?
Anladım hocam. Teşekkür ederim.
Okay. Okay. So today we have the exam, and it is relatively easy, so don't worry.